Good evening, everyone, and welcome to our second webinar. And I just wanted to welcome you all again and thank you so much for joining us. We actually do just want to remind if you have any issues with logging on, it does work better from a computer and from the browser. So if you have any friends who are trying to log on still, definitely check in with them and let them know. But we are hoping to stick to time today. So I want to go ahead and walk through our agenda with us. And for today, we are welcoming you. We also will have our introductions of our speakers. You see somebody extra with us today. And we're going to walk through some background and orientation on our topic, which is the groundwater flow model. An introduction to just groundwater flow and what modeling means. And then we're actually going to walk through that model as well. So we will have a Q&A section at the end too. And then we're going to kind of cover some of our upcoming events. So you'll hear a bit more about that in just a minute. And but generally, we're mostly going to spend time just on giving you information so you can understand more about our work that we're doing with understanding the groundwater flow. So I wanted to jump right into our introductions. Hello again, I am Lila Castellano. I'm a civilian community liaison here with the environmental and remediation team of Navy Closure Task Force. So I grew up in the Southeast on the mainland and I'm now here on Oahu and very excited to be part of the team here. It's definitely a privilege to be here and have an impact on something so important here on our island. So I'll be facilitating the webinar today, helping with the Q&A section. And now I want to pass it on to Commander Dunn.
Aloha and good evening. I'm Commander Ben Dunn, a Civil Engineer Corps Naval Officer originally from Aiea, Hawaii. I've been given the distinct privilege and opportunity to lead the Environment and Remediation Team at Navy Closure Task Force Red Hill. And I'm excited to be speaking again today. And today, along with the help of one of the Navy's consultants, we'll provide an overview of the Navy's groundwater flow model for Red Hill. In addition to our key speaker, Ms. Bianca Mintz, we have a few other scientists online today to help with question and answers perhaps later on. And Bianca.
Hello, everyone. My name is Bianca Mintz. I am a licensed professional geologist specializing in hydrogeology for the Navy. I actually grew up in New York City, but I completed my bachelor's and my master's at UH and have lived in Hawaii for 12 years now. I am so excited to talk about the results of our groundwater modeling efforts and Hawaiian geology and a lot of other interesting topics today.
Right, so that is us today. I know we went over this in our last webinar. If you weren't able to see our last webinar, it is available on the Safe Waters website, and you can also find it on the Navy Closure Task Force YouTube channel. But just want to give you a picture of our team and how we are structured with the overall Navy Closure Task Force. So our department is a team of scientists and engineers. We're part of a larger organization that is the Navy Closure Task Force Red Hill. You'll see on this slide kind of a circled green area. That's our team there. So the Navy Closure Task Force Red Hill officially took over the Red Hill Bulk Fuel Storage Facility from the Joint Task Force Red Hill in late March of this year. And our team is composed of nearly 200 personnel made up of active duty service members, reservists, civilians, and contractors. So good representation of everyone right here. And civilians are experts from multiple fields, all volunteered to join the task force, all are permanent employees. We're here for the long haul, and we're definitely committed to our community here. Our mission is to decommission Red Hill and conduct long-term environmental remediation efforts in coordination with stakeholders to protect public health and the environment. So this hopefully gave you a good picture of who we are in the bigger picture. And so today's webinar is a larger part of a larger effort by the Navy Closure Task Force Red Hill to stay connected with our community and share information about the work the Navy is doing. So you see here some of the ways that we have to connect with the community. So I'm just going to run through a few of those options. For me as a community liaison, I'm out in the community a lot, and so I love all the different ways that we're sharing information because I know people need to understand what's going on here. So we have begun hosting these webinars and have supported also the EPA's webinars as well. So wonderful ways to get out a lot of this technical information so we can share it with you. We are just starting up also a podcast. So I mentioned the Navy Closure Task Force YouTube channel. I definitely recommend going there and checking out the different podcast and podcast episodes that we have there. Great little short videos just showing it different aspects of the Navy Closure Task Force process. And it's called Let's Talk Red Hill. So go check those out. The Navy also regularly hosts information booths about drinking water throughout the Joint Base Pearl Harbor Hickam and the communities served by the water system. That's me actually, so you'll see me at those info booths. Our next ones coming up are on the 29th of October at the NOAA facility on Ford Island, and then also the 30th of October at the Capelina Night Market. So hopefully you can come by, I can answer any questions, look up sample results, things like that. And then one of our favorite ways to engage more deeply with the communities are our open houses. So we host those quarterly, and our next one is coming up mid-November. So I definitely recommend looking up when you have more information announced. We do have our calendars posted on the Safe Waters website as well as the Navy Closure Task Force website. And then we attend numerous community events every month. So please visit our website so you can see the Navy Closure Task Force has a very long list of all the different places that we're represented and that we're involved in. So I definitely recommend checking that out if you want to touch base with somebody or attend one of those meetings. And then lastly, we have our websites as our go-to place for sharing the most recent updates. So we share all of the water monitoring and groundwater monitoring and all of the technical information on our Safe Waters website. You'll see kind of two options there, the drinking water side and the environmental side. So great place to explore. And then also the Navy Closure Task Force website has all the information on that bigger picture of the closure of the facility. So highly recommend checking out all these options if you're interested in learning more about what we do. And so lastly, you may see us throughout media doing interviews and things. We always want to try to connect as much as possible. Our teams are the more technical side, so you may not see us on TV as much or in interviews. We try to leave that to our public affairs team. You're going to hear from some wonderful engineers here. Let's jump right into that information now. So if we want to go to our next slide, we're actually going to get started.
Okay, first I'd like to give a big picture look at the Navy's groundwater flow model project. The Navy has developed a groundwater flow model to advance our understanding of the local conditions at and around Red Hill and in the Halava Valley, and to better understand potential migration of released fuel and to inform our environmental cleanup efforts. The Navy's model is a complex, comprehensive model comprised of several supporting models. The model is dynamic and developed through iteration or repeated steps. It's informed by data collected from newly installed groundwater monitoring wells through other studies and field efforts, as well as stakeholder feedback. In 2020, the Navy submitted its initial groundwater flow model to the Hawaii Department of Health and US EPA for review, feedback, and approval. In 2023, prior to defueling the Red Hill, the Navy submitted an updated model based on data collected since the first model, as well as information available at the time and feedback from the regulators. Just last month, the Navy submitted an updated model for the review and approval of EPA and DOH based on feedback and additional data collected from monitoring well installation, boring logs, data collected over the period of the previous 18 months. And in parallel to the Navy's effort, the University of Hawaii has been conducting field studies this year to develop an independent groundwater flow model, which the Navy looks forward to reviewing and understanding. Again, it's an iterative process, and information made available from these efforts will further inform the Navy's model over the coming years. It's basically a living document. Each version of the model is more informed and therefore is more telling. I'm going to turn this over to our key speaker now, Bianca, to provide an overview about groundwater modeling in general and our current model. Next slide.
Before we jump in on that, Bianca, I just wanted to let you all know we do have our Q&A section. So before we can jump into all the technical information, that should be open if it's not already. And so if you have questions, feel free to submit them throughout. We do have our team that's helping us with those questions, and so they'll be reviewing them and getting them ready for the Q&A section. So definitely feel free to submit any questions as we're presenting information. So we'll have those prepared for us. So thanks, Bianca.
Okay, thank you, Lila. Commander Dunn. It is an honor to be here today. So today, we're going to talk a lot about groundwater models, including types of models, methods for modeling, results of our efforts. To better understand all this, we're first going to just take a small dive into groundwater flow and aquifers. So we'll just play this video first and have a listen, and then move on to some more site-specific topics.
Aquifers are rarely underground lakes like you might see in a cave. They are typically rock formations that are mostly solid, but like sponges, they have interconnected fissures and pore spaces that hold water and allow it to move within the formation. An aquifer is best defined as a layer of saturated rock and the water in its pores. Aquifers are formed very slowly over vast periods of time. Water in aquifers comes originally from the surface of the earth. When rain falls, some of the water infiltrates underground and collects in the pore spaces. Water in rivers and lakes can also seep into the subsurface pores. Eventually, some interconnected pore spaces become saturated with water. In other words, they become an aquifer.
The ability of an aquifer to produce water depends on the properties of the aquifer's rock formation. The two most important properties are porosity and permeability. The porosity is a measure of the volume of empty space, or pore spaces, inside the rock. Pore spaces can be openings between grains, fractures in the rock.
All right, we will pause it there.
Aquifers are...
Go to the next slide. Okay, so that was a little bit about groundwater flow. So now we'll move into groundwater flow models. So what is a groundwater flow model, or a model in general? The best analogy we could think of is when a meteorologist goes on TV and they have a hurricane tracking map. There may be different paths of the hurricane or an error bar, say, around where the hurricane is going to go. The meteorologist uses a model to predict that. In a similar way, we use computer models to simulate and predict the flow and direction of groundwater in an aquifer. Again, an aquifer being a body of rock or soil that holds groundwater. Really, all models are simplifications of real-world phenomena using physics and mathematics. They are based on inputs and outputs into the system. Next slide. So an input adds water into the system, also known as a source. An example could be a large rainfall event. An output, known as a sink, withdraws water from the system. Examples include pumping wells or supply wells or natural springs. These inputs and outputs can affect the groundwater flow and direction. For example, if you have a pumping well that's withdrawing water from your aquifer, the flow field or orientation will move towards that pumping well. Next slide. Now, there are many different types of models in our field. For example, we have groundwater flow models, which estimate speed and direction of groundwater flow. There are vadose models, which estimate the movement of fluids to the water table. The water table is at a certain depth in the ground surface. Below the water table is saturated, or the aquifer, with water. Above the water table, there isn't any water. So any fluid that is released from ground surface or above that water table, we would use a vadose model to estimate how or if it moves down to the water table. And then we also have contaminant fate and transport models. These are used to estimate future or past concentrations of chemicals. The fate represents how the chemicals degrade or undergo any degradation or biodegradation. The transport is where the chemicals move, largely based off of the speed and direction of groundwater flow determined in a groundwater flow model. Now we know that oil and water doesn't exist, and petroleum-related chemicals interact with soil and rock in a way that they typically don't flow as fast as groundwater does. Today, we're going to focus on two core models, our groundwater flow model and our contaminant fate and transport model. Next slide.
Just to clarify on that one, I think you might have said like oil, it doesn't exist, but I think you meant doesn't mix.
Yes,
Yeah.
oil and water doesn't mix.
Perfect.
Yeah, oil and water does not mix. When we develop our computer models, we need to determine the level of detail that we're looking at. For example, all of these topics here can be mixed and matched. So you could have, say, a two-dimensional model with uniform geology and very few changes over time. Our model is complex and advanced in that it is highly detailed. It is three-dimensional. It accounts for highly variable geology, specifically for our Hawaiian geology that we're trying to represent. And it includes many changes over time when pumping wells, say, turn on and off, or even large rainfall events. Next slide. When building a model, it is important to determine the parameters that are input into that model. An example of this is the properties of the soil or rock. Some properties include hydraulic conductivity, which is how easily soil or rock can transmit groundwater. You also have porosity, which is how much space or pore space there is between soil and rock particles. This photo here is of the Big Island. In the middle, you see a massive pore. We can see there are very little pore spaces, and so groundwater tends to move slower through that material. Contrast that with the clinker units above and below that pore. There are more pore spaces and groundwater can flow quicker. Another parameter to consider is the properties of our chemicals. Does our chemical adsorb or stick to soil and rock? Does it decay or break down naturally? And is it soluble? Will it dissolve in groundwater? A lot of information, as you can see, is needed to account for site conditions and build a model. Next slide. One of the things we really focused our time and energy on was representing the Hawaiian geology in our model. Volcanic rock properties can vary greatly over short distances. In the image to the right, we see a massive sequence. Over a very short distance, we go from massive to clinker to massive to clinker. We get a lot of our data from rock cores. Rock cores are collected when we install monitoring wells. On the bottom left, you see two images of rock cores. They are approximately 4 inches in diameter, and these boxes are about 2.5 feet long. The bottom box is a massive core. As you can see, there are very few pore spaces, so water likely moves slower through that material. The upper box, the upper row of the upper box, again is a massive However, if you look at the lower right of the upper box, then that's an clinker, similar to a gravel. There are more pore spaces to facilitate faster groundwater flow. Next slide. Another type of basalt or lava flow that we see at the facility and around it is a pahoehoe flow. The upper left image is an outcrop of a pahoehoe flow, and the bottom right is a box of rock cores of pahoehoe. Compared to the other boxes, you can see that there are more pore spaces and interconnected fractures than, say, the massive meaning water could move relatively quicker. However, there is less pore spaces than with an clinker. Pahoehoe tends to transmit water at a relatively medium rate compared to the other basalt flows. Next slide. Another material we observe is saprolite. All three of the basalt types we just discussed can be weathered to a saprolite, which is weathered in place and retains its rock-like appearance. Due to the soil grains and clay content, saprolite tends to transmit groundwater at a slower rate than a basalt. Next slide. Moving on to model development. Initially, we start with data collection. Vast amounts of groundwater, water levels, chemical concentrations, and geologic properties have been collected by us over decades. From there, we develop the model using input from various experts, companies, SMEs, and agencies over the course of decades. We also wanted to run many simulations. So over the past few years, we worked to account for many different potential conditions in supply wells and geologic formations to get a range of answers and possibilities. Next slide. Now looking at our model area. So first, we start with the island of Oahu. The orange area is the Red Hill facility boundary, and the yellow boundary is the model area that we investigated. Note, this boundary is much farther than the Red Hill facility boundary. Typically, it is best practice to push your model boundaries farther than your area of interest. At the top, we wanted to start at the Ko'olau mountain range, where a lot of precipitation takes place. We put our other boundaries along streams or watersheds and then down into the ocean. This boundary should not be confused with the area of anticipated chemicals, as it extends far beyond any likely impacts. Next slide. So now we're getting into groundwater flow a bit more, specifically in Hawaii. So this left image, again, the yellow boundary is our model area or domain. The orange boundary is our Red Hill facility. So groundwater in Hawaii typically flows from Mauka to Makai, or from the mountains to the oceans. We also note that there can be localized variations of overall groundwater flow. Another concept for island groundwater flow is our freshwater lens. The island supports a freshwater lens that supplies our drinking water that sits atop saltwater. The higher up the mountain or the ridges that we go, the thicker that freshwater lens. As we move closer to the ocean, that freshwater lens tends to pinch out and move and give way to saltwater. Next slide. We really wanted, when developing this model, to look into a variety of combinations and scenarios to account for as many possible results as we could. To do this, we looked at different combinations of water supply wells or pumping rigs. Again, the image to our right is our model domain. The light green dot represents the Navy Red Hill shaft. The purple or pink green dot is the Board of Water Supply Halava shaft. The dark green, again, is our Navy IAEA Halava shaft. And then towards the western end or left portion of the image, we have our freshwater springs. So we accounted or looked into what happens when Red Hill shaft is shut off, or when Red Hill shaft is pumping at 1.8 million of gallons per day, as it currently is, or when Red Hill shaft is pumping at 4.3 million of gallons per day, which was the pumping rate after November 2021. We looked at Board of Water Supply Halava shaft when it is off or not pumping, or when it's pumping at its permitted capacity of 12 million gallons a day. And we also accounted for Navy IAEA Halava shaft, both when it's off and it's pumping at 0.8 million gallons a day. So now we're going to get into some of our results.
I do want to just clarify for everyone here, these are scenarios, and so this is not real life that we're looking at. And also to clarify, the Red Hill shaft is not currently connected to our water system. So just want to clarify that for everyone as we're talking about it being pumped and things. These are scenarios that they have used this model to create, but also, you know, it's not connected to our water currently.
We wanted to account for as many scenarios as possible to get a range of results. Next slide. So now we're going to get into some results. This is one set of results from one scenario. In this scenario, again, it's theoretical, not actually what's going on right now. We have Red Hill shaft pumping at 4.3 million gallons per day, and Halava shaft is off. The blue lines represent groundwater flow. And what we observe is groundwater flow is largely from Mauka to Makai, but there is also a small component of westward flow towards the springs. This is influenced by weathered geology or weathered basalt closer to the ocean and farther down from the ridges. The model shows that groundwater flow does not travel cross-valley directly from the facility towards the Board of Water Supply Halava shaft, but rather from Malka to Mackay at a westward angle, from starting at the mountain or the ridge line for the Ko'olaus. Another thing to observe is that when Red Hill Shaft is pumping and drawing water, it pulls from the Moanalua Valley to the east. Water outside of our capture zone is also looked into. If you notice, there is one blue line just past Red Hill Shaft. Water that is beyond Red Hill Shaft will travel towards Pearl Harbor and the Springs. Typically, it travels at a much slower rate due to the weather geology in that area than at rates from the top of the mountains. Next slide. So now we're going to play a short video. You can press play. What this represents is each arrow is a year in time. What we can see is groundwater moves at approximately a little over 10 years from the top of the mountains down to the Red Hill facility. We also observe that groundwater again moves at a much slower rate from Malka to Mackay along our path lines once it gets into that weather geology, as we can see with that little particle. Now, once this particle makes its way to Red Hill Shaft, again from the top of the mountain range, we'll see what happens with water past Red Hill Shaft. What we observe, right there it goes, is water moving towards the Springs or Pearl Harbor, again at a much slower rate. It can take over 30 years from water to move from the top of the Ko'olau mountain range from Red Hill Shaft down to the oceans and springs. Just let that play through there. All right. So again, you could go to the next slide. There we go. Next slide. Thank you. So again, that was just one of our many scenarios that we looked into. This is another scenario, again, not currently taking place, in which we said what would happen if Red Hill Shaft was off and Halava Shaft was off. All of our QL was off and not pumping, not acting, again, as sources, as sinks. Where would our water flow? So what we observe, again, is Malka to Mackay flow from the mountains down towards the oceans. Pretty similar with a small westward flow direction towards the springs. Again, we do not observe any cross-valley flow in our model from Board of Water Supply to Board of Water Supply Shaft from Red Hill. Next slide. So we'll play a similar video again with our arrows. And we can see, again, it takes about 10 plus years for water to make its way from the top of the ridges through our area. You can see arrows are moving. Again, the water is coming from the mountain range. Water at the facility is moving down the ridge towards the ocean. And it can take, again, a few decades for this to take place. Next slide. So now we're going to look at another scenario. Let's look at what happens to groundwater flow even more locally at the Red Hill facility. The model predicts that groundwater under the tank farm will be captured by pumping at Red Hill Shaft. So if we look at this arrow here, and we can use the corner of it to show that, Red Hill Shaft pumping at 4.3 million gallons a day with Halava Shaft off tends to make its way towards Navy Red Hill Shaft from under the tank farm. Perfect. Okay, go to our next slide. So we spent a lot of time talking about groundwater flow. So let's move a little into transport and how chemicals move in our groundwater. Generally, we know that petroleum-related chemicals do not travel as fast or as far as groundwater. Next slide. So here are some diagrams showing chemical transport processes. The upper diagram shows groundwater flow through a rock or soil. As we've discussed, depending on the flow path and the porosity and the grain sizes, groundwater can move at different rates, as shown in the red arrow at the top, or maybe it would take, say, a slower path from the green arrow, or something in between with our blue arrow. Once you add a chemical to the mix, There's another factor or parameter to consider. Will the chemical absorb and stick to the rock material as that red dot is showing? Or will it move with groundwater as the green dots are showing? And when it does move with groundwater, how fast will it move? And again, typically we see that petroleum-related chemicals will move much slower and not as far as groundwater. So next we'll talk briefly about our contaminant fate and transport modeling results. Next slide. Again, we ran many scenarios and simulations to get a range of results. To be protective and account for uncertainties, we made a number of conservative conditions into our model. We built this in because we wanted to really take a conservative approach. For one thing we considered is the source of our chemicals that we modeled was much larger than what our monitoring data indicate. Specifically, our models simulate likely scenarios that we use in conjunction with actual data from our monitoring well network. We took that data and increased the results in our model just to be conservative. Our chemicals were also modeled as if they don't degrade or break down, even though we know that they do. So again, we modeled much larger chemicals and we modeled them in a way that they wouldn't break down. This is considered a very cautious overestimate of migration and extent. Overall, we found that the model does not predict groundwater quality impacts to municipal water supplies. And those are all the slides that I have. I'll toss it back over to Commander Dunn.
Okay, thank you. So again, our groundwater modeling effort is an iterative effort. It is a living document that the Navy will continue to improve over the future as we learn more from the ongoing studies and additional data collection through our well installation and groundwater monitoring efforts. As we move ahead, the Navy looks forward to the regulators' feedback on its most recent submission of the updated groundwater flow model. And we will post a redacted version of the updated groundwater flow model report online on our environmental page of the Safe Waters website sometime over the next month. And additionally, as more data and information is gleaned from the new monitoring wells and continuous field studies, the completion of the University of Hawaii's independent modeling effort, the Navy will generate yet another version of the model at that time. And thank you again, Lila.
All righty. So we are going to jump into our Q&A section now. I know we do have some questions already kind of queued for us, but please feel free to continue submitting those as we continue through this time. So we do have our ending time set for 6 o'clock. So we'll definitely go through as many questions as we can. If we're not able to cover all of those, we do plan to hopefully get answers posted to remaining questions or things that we weren't able to answer today, posted to a page on the Navy Closure Task Force website. So definitely submit your questions as they come to you, even if it's close to the end of our time. And so I do want to go ahead and just jump in. And just one last reminder, as you see on the screen here, we are trying to keep all questions relevant to our topic today, just because this is what we have the time for today. So just feel free to submit those as we go. All right, so our first question was kind of already answered by Commander Dunn just now, but we have a question asking, can we get a copy of the groundwater flow model report and data? And so I think if you want to run over that answer again for us.
Certainly. So as the Navy submitted its most recent version, the updated groundwater flow model to the regulators in late September, we are working to produce a redacted version. A redacted version of the report is a version that screens for defense critical infrastructure information. So that report copy will be made available on the Safe Waters website, again on the environmental page side, sometime in the next few weeks by November.
Okay, thank you. All right, and then we have another question. Where are the test wells located in relation to the estimated direction of groundwater flow? So is that something we can answer tonight?
Certainly. So our monitoring well locations are scattered around Red Hill, along the facility, along the core of the facility, the boundary of the facility, And we have what's called sentinel wells, which are installed offsite in between the Red Hill facility and drinking water production wells, both the Navy and local community production wells in the Halava and IDEA area. And if you want to expand further.
Another, so we do, as Commander Dunn said, we do use all of our Navy wells. We also utilized data from a number of other wells. So DLNR provided data into this, USGS provided data into this, and those wells are also in the facility as well as throughout our entire model area. So that entire yellow area, again, most of the monitoring wells are more concentrated around the facility, as Commander Dunn said, but we do have data from other entities throughout.
And I do suggest we have our previous webinar that we had last month. And so you can find that again on the Safe Waters website. It's under our media library or on the Navy Closure Task Force YouTube channel. So that actually covers the monitoring wells specifically. So if you want more information on that, I definitely recommend going to that one. So for our next question, and thanks for sending these in, they're coming in, it's great. If there are actual data points, where are they available for review? So it sounds like that will be available in the report.
Correct. So the updated model report is really the one-stop shop for summary of that information, for groundwater monitoring well information, and that data that's available on the environmental side of the Safe Waters website as well. That had helped feed into the model.
Okay. And then how did you derive the blue flow lines? Were they from actual measurements or is this theory? So if you guys want to jump into that.
So first, we start with thousands of actual measurements or data points, and we input that into the model. And that includes water level data, as well as the geology that we drill through when installing monitoring wells. We then also save some data to use for our calibration. So we then calibrate our model after we input our data. We then use additional data to calibrate it towards that actual data to make sure our results are statistically significant.
Okay, thank you. Right. Looks like we've got a lot of questions coming in, so this is wonderful. I know this is definitely very new information for everyone, so I'm really glad we're asking the good questions. So our next one is some degradation products may move faster than the original petroleum. How are you accounting for those products?
So at this time, we are always collecting new data and looking into new data. We took a very conservative approach in that we modeled products that move at a slower rate than groundwater. We can account for additional data in the future as it comes in, but at this time, we felt it was best to not include biodegradation that would decay a product. And instead, we also, another thing we did is we greatly increased the source of the contamination in our model. So it's much larger than what was actually monitored currently in our data. So that should also account as a conservative measure for this. But as Commander Dunn said, this is an iterative process and we are always adding new data and including more information in our models as we progress.
All right. So going on to our next question, is the groundwater model based on actual real world model, or is this just estimates as repeated in the presentation?
So the model is based on actual data, thousands of data points that we've collected over decades, water levels, geologic data, chemical data, and we also calibrate or check our model. Another good way to describe calibration is checking. So we check after we input our data and then run, say, a theoretical simulation. We then check it against actual data to see if it's statistically significant and if it's reasonable. And if not, we go back and we make adjustments to make sure it's actually representing the data we collect. And if it is, we move forward. Another thing, when we say theoretical, what we mean by that is, as Lila said, is not actually happening now. So when we look at 4.3 millions of gallons a day at Red Hill Shaft is not pumping right now at 4.3 million gallons a day. It's 1.8 million gallons a day. And again, that's not actually connected to the water distribution system. So we're testing for these scenarios to see if that were to take place, what could we expect? Where could we expect groundwater to flow? Again, always corrected and calibrated to actual data that we collect in the field.
Right, thank you. And our next question, why hasn't the EPA approved any of the Navy models since it was required back in 2015?
So the Navy first submitted its groundwater flow model report in 2020. It was early in the process. Since that time, we have collected additional data, refined the model that has gone in. We produced an interim update in advance of defueling to make sure we had a more updated model before we started that higher risk evolution. And we've again submitted a more recent version just in the last 30 days that's even more informed. And we look forward to the regulators' feedback on that version.
Okay. And this next question, more of a back of house question. So somebody jumped on a bit late and they want to know if the presentation was recorded. It is being recorded, and we will have this posted on the Safe Waters website as well as the Navy Closure Task Force websites. It will be in the media library. So we're definitely going to have this posted for your reference, and we're hopefully going to have the PowerPoint itself posted too. So you'll have these available as resources. All right, so our next question is, what is the review and comment period for this upcoming groundwater flow model report?
So the regulators have the report. They've received it at the end of September. They will have about 60 days to look over and provide their assessment of the model. We continue to have dialogue with both the EPA and DOH and other key stakeholders as we have gone through this process. And it's a continuing dialogue. We expect to hear from both DOH and EPA sometime next month about our model. At the same time, we'll be providing that redacted version online.
Right, and then our next question, is there also a tracer study that was done, and can that be made available to the public unredacted?
So outstanding, great question. So as part of the parallel effort that's independent of the Navy, that's the University of Hawaii's groundwater flow modeling effort. They have been conducting studies since earlier this calendar year out in Pearl Harbor and the environment in the Halava Stream, and then have since moved on into the facility as defueling has completed, and they've begun additional studies. They're in the final planning stages of conducting a dye tracer study here this winter in the facility, and we greatly look forward to the results of that because it will certainly inform their effort, but we anticipate learning more from what the conclusions are and what that data will show us in the coming months.
Right. Thank you. So this next is a comment. The blue flow lines question is first, and then the data points question. So if there was a question that should have been submitted with that, please feel free to resubmit it so that we can further answer your question for you. All right, so I'm going to move to the next one from there. Was the Board of Water Supply, or BWS, consulted on this groundwater model? Were there comments and suggestions included in this model?
So yeah, since the beginning of the Navy's groundwater modeling efforts, the Honolulu Board of Water Supply have been identified as a stakeholder along with other parties, the U.S. Geological Survey, and so on, and have been invited to participate in providing feedback on several iterations of the model. We do that through the provision of redacted documents, so those documents have been made available. We've also through confidentiality agreements that need to be in place, that option is also available so that we can have those sensitive discussions with respect to the infrastructure. So that opportunity does exist out there.
Okay. And again, thank you. These are wonderful questions. So
They're great questions.
I appreciate everybody being involved and really wanting to understand. So this next one, there's a few questions all together here. So will the groundwater flow model files be released to the public for its review along with the report in 1 month? And next part to that, did you use a mod flow computer program and run particle track simulations with Board of Water Supply Halava shaft pumping at 12 million gallons per day? So let's take that first question, just whether the data and everything will be there, and then we can move to the next one.
Yeah, certainly. Great approach. So for the report, so the report will be made available, of course, as we've mentioned. The file itself, it has embedded information that's telling of that's sensitive. So those files itself won't be made available or generally available. Certainly have been provided to the regulators for their review. But we look over the coming weeks, we'll be looking for additional ways to share more information and details about the model with the public, perhaps via the website. But that discussion and planning will continue. I'm going to turn it over to Bianca for the
I'll just repeat the second question for you. So did you use a mod flow computer program and run particle track simulations with BWS Halava shaft pumping at 12 million gallons per day?
Yes and yes. So we use ModFlow USG specifically for this work. And we did run particle tracking simulations. And for those in the audience, those particle tracking is when you drop a particle of water, not contamination, and track to see where it would flow. And that's how you develop the blue flow lines that we were showing today. And we did run scenarios with Board of Water Supply Halava shaft on at 12 million gallons a day. And we ran that for what happens when Halava shaft is on at 12 million gallons a day and Red Hill shaft is on, as well as even more conservative when Halava shaft is on at 12 million gallons a day and Red Hill shaft is completely shut off. And we did look at where particle traces do go under those scenarios.
Thank you.
Those will be in the redacted report that will be released.
Right. And so continuing on, we definitely have a lot of questions. So hopefully we'll be able to get through these. But like we said earlier, as we go through, if we're not able to reach all of the questions in the time we have today, we are saving these questions and tracking them. So we will hopefully get some answers to you on the Navy Closure Task Force website. So we'll let you know from there. So for our next question, we have, how did you deal with the calibration of the hydraulic conductivity in the groundwater model, especially regarding the vertical and horizontal
anisotropy.
And they actually say thank you, so you're welcome.
All right, get technical quick.
Okay. So this was actually really important to our model development, and honestly, one of my favorite parts of the model. And working on it, just to be completely honest, we took our geologic data from monitoring wells, and those rock cores, we logged those to, they're hundreds of feet. We logged them to the 10th of a foot in levels of detail. And we took that detail and we used a research code actually recommended by the EPA SME. So we are working in collaboration with them to get the best product to the public. So we use their suggested research code to develop what we refer to as realizations or different possibilities of the geologic makeup of our model. So specifically around the Red Hill facility, we incorporated the very detailed geologic logging, and then we used a statistical computer simulation to almost, if you will, fill in the gaps between where our monitoring wells are and where that geology is to account for all of the variations in geology. And that, we ran that 50 times to count for 50 different possible scenarios. And of course, we checked it again against our rock cores. So some rock cores went in and some rock core data was used to check it. And really, it's that anisotropy that pushes. If you remember when we were looking at our blue flow paths, largely flow is from Malkuth to Mackay. But locally, we have that slight westward component, and we contribute that to the anisotropy. Anisotropy, to define it, a good analogy that I was taught, if you have, say beach sand, right? Evenly sized pieces of silica, water is going to typically flow through it at a relatively even rate. When you look at some of the rock pores we showed, the pieces of rock are all different sizes, right? The pore spaces, some are elongated, some are rounded. The gravel has larger spaces, the masala has smaller spaces. And so that water isn't going to necessarily move at a uniform rate. And that's where you really factor in that anisotropy factor, which causes water to move, in our case, from what we found, at that slight westward component. So hopefully that answered that really fun question.
All right, and we now know how to say anisotropy. Okay, thank you. So our next question, what did petroleum-related chemicals mean? So the phrase petroleum-related chemicals mean within this presentation. Are they analytes like BTEX or JP5?
So we look at many chemicals that might be of concern based on the material stored at Red Hill, and those chemicals of concern are what's represented by the model.
Yes, specifically the contaminant fate and transport model looks at total petroleum hydrocarbons, which is not a BTEX. We do sample for BTEX and we do account for naphthalenes and all those other petroleum related chemicals, but TPH really is our biggest analogy for JP5. So just a little bit about TPH. The difference between TPH and say a BTEX. A BTEX is a chemical that you can determine the presence or absence. So if you get, benzene is the B in BTEX for that acronym. If you sample and get a result for benzene, you have the result for benzene. For total petroleum hydrocarbons, that is a range of carbon-based material, which JP5 is. So when we sample our monitoring wells for TPH, we can get a concentration of TPH, and then we go a step further and we look at what's called a chromatogram, which is a diagram that shows a pattern, and we look at the patterns, and some patterns will be indicative of JP5. And so those are the patterns so it's just an extra step with TPH that's required than a strict benzene presence or absence. TPH could be a wide range of anything carbon-based. So coconut oil would come up as a TPH. Cigarette smoke would come up as TPH. So JP5 as well is another one of the many components that could come up as TPH. But again, it can have a really clear signal for JP5 when run through that additional analysis to look at that fingerprint. So that's specifically the chemical that we looked at.
Thank you. All right, and the next is a request accessing to the tracer study. So if you want to just remind where that tracer study would be found.
So yes, the University of Hawaii is conducting that effort. So we don't have that data, those results. We look forward to obtaining that soon. Sometime in the coming months, we'll be receiving that. So looking forward to it.
Right. Now I know we are probably not going to make it through the rest of the questions that we have. We just have a few minutes left. So just a heads up on that before we go through, but we're going to try to make it through as many as we can. So our next one, it says, but the degradation of products may move faster and therefore reach the springs sooner, Board of Water Supply wells sooner. So why not follow those products now?
So we developed this model with a large group of experts and different stakeholders and the regulators as well. And contractually, or per the AOC, it was essentially told to the Navy that we would look and model TPH. So that's where we started. As Commander Dunn says, this is an iterative process. We look forward to working with the EPA and the Department of Health and many other stakeholders to potentially do additional work in the future and incorporate different data. But at this time, we were going with the AOC requirements of modeling TPH.
Okay, great. I think this is all important information for all of us to understand as we look at this information. So our next one, theoretically, the water could flow a sharper westward direction due to the geology. So not really asking a question, but that's the statement.
So what we showed today is what our model predicts. We continue to collect new data. It's an iterative process. We look forward to incorporating more geology from more monitoring wells and more rock cores. We look forward to incorporating results from UH's tracer study and again, continue to update as we get more data. But at this time, this is what our model and our data are indicating presently.
All right, and our next one, do you still believe that the aquifer would be considered a sole source aquifer based on your recent information collected in the watershed?
So we don't really designate maybe I'm not understanding the question. We don't really get to determine whether an aquifer is classified as sole source or not.
Yeah.
It's an interesting concept to think about.
So it looks like that might not be quite a question that we can answer here. If you wouldn't mind maybe clarifying what is a sole source aquifer, and that might be some context that will help people.
So I could just define that. So a sole source aquifer is designated by the government as it's pretty much what it sounds like. It's the only available aquifer or drinking water for a region. So for Oahu, because we are an island, right, our aquifer is a sole source per the government, and we would agree with that. It is the only aquifer. It is our only freshwater resource on this island, which is why it is very important. As for how those determinations are made, I believe that that is probably beyond the scope of our power here.
All right. And I think we're just going to do a couple of more questions depending on how quickly we get through these answers. Based on the groundwater model and data that was collected, are there contaminants flowing from Mauka to Makai?
Large contaminants. Okay, so we talked about how, I'm just thinking through the question. We talked about how groundwater typically flows from Mauka to Makai. Looking at our contaminant fate and transport, so regionally, water tends to regionally Mauka to Makai, more locally around the Red Hill facility. Groundwater is also Mauka to Makai towards the Red Hill shaft pumping well. Then when you factor a contaminant or a chemical in there as well, that would go with the groundwater from what we observed. So again, when Red Hill shaft is on, the model predicts that chemicals are pulled towards Red Hill shaft, which is Makai of the facility and the tank farm. Therefore, yes, Mauka to Makai.
And I don't know if we'd want to speak just to clarify that. We talked about this in our last webinar, but just what is happening right now at the Red Hill shaft with the pumping for any contaminant that might be there.
So yeah, so the Red Hill shaft has been continuously pumping. We've continued to pump it since January 2022. It was for close to 20 months, up at the over 4 million gallons a day rate. Earlier this spring, we've reduced that rate, but what the Navy's assessed is has created a localized capture zone at the Red Hill facility, which would draw some of the groundwater up and out. And so any chemicals that are present there, the concept is that's being extracted out, treated through their granular activated carbon treatment system that's on site at the facility, and then discharged into the local stream as clean water. But the data that we've collected over the past few years of our groundwater monitoring wells, and again, we're continuing to drill those as we've covered in the other webinar. The data, we're getting that in every month. we're not seeing contaminant migration off the facility. We're not seeing in these other sentinel wells and other locations beyond the Red Hill facility of these chemicals of concern.
Okay, thank you so much. All right, so we are actually at 6 o'clock right now. We can go for a few more minutes. So just going to run through kind of our last, just letting you know where else you can talk to us. I know we've got a lot of questions, so some of these other opportunities where you can reach the Navy Closure Task Force might be good opportunities to connect some more. And so just wanted to remind of those. We do have other webinars that we hope to do in future. So we don't have specific dates for those yet, but we will be announcing them, and hopefully we'll get them out to you ahead of time so you'll be able to plan on attending. And so be on the lookout for those. Our next info booth, like we said earlier, will be at the NOAA facility on Ford Island. So that's on the 29th of October. And then we also will be at the Capelina Night Market on the 30th. And then mid-November will be our next open house. So that date should be announced soon. I would say the open house is probably the best place to come and really ask some questions. We're going to have several representatives from the Navy Closure Task Force Environmental and Remediation team there. So you can speak directly to our engineers and all of our team of scientists. So they'll be able to answer lots of questions. So definitely recommend planning on that. And then we also have our podcasts available talking about other aspects of the Navy Closure Task Force response to closing the Red Hill facility. So definitely check into those. I know we've got a lot of questions here, and so people are wanting information. So hopefully we're able to get that out to you and be able to answer questions that you have. So thank you again for joining us tonight, and we look forward to seeing you again soon.
Aloha. Thank you.